Assalamualaikum and a very good morning. I bid to Dr. Haslina and my fellow friends. Today we are the last group 15 are going to present about the first row transition metals, hydride. So my name is Latifah binti Muhammad Hassan and my metric number is 207643 and my friend is Nur Sazwani binti Zakaria 207061 and my other friend is Suharni binti Muhammad Nur 206997. So let's start. So, hydride consists of three types, which are ionic, metallic, and covalent. Metallic hydrides are formed when hydrogen combines with D block or F block elements. Some of D block elements do not form hydride, which are from group 7, 8, and 9, called as hydride gap. In the lattice, there is space between atoms of metal. This space is called an interstitial site. Since hydrogen fills up interstitial sites, metallic hydrides are also called interstitial hydride. So this is the periodic table that shows about the hydride on the first row transition metal from scandium to zinc, and the manganese, ferrum, and copper does not form metal hydride. So the characteristic of metallic hydride is stable in water, is more brittle, and it can conduct electricity but not good as their parent metals. So it is strong reducing agent due to their interstitial hydrogen. So the uses of metallic hydride is widely used in industries. They also use as sources of energy. And this property used for catalytic reduction in the process of hydrogenation.
Okay, so today I would like to present about covalent hydride. Hydrogen is a unique element in the periodic table. It is the only element that can donate, gain or share electrons. When hydrogen share electrons with other elements, it forms covalent compounds called covalent hydrides. So some examples of covalent hydrides are H2O, CH4, NH3, HF, MgH2, BeH2, and etc. In covalent hydrides, hydrogen shares electron with p block elements, so some s block elements like beryllium and magnesium also covalent hydrides. The characteristic of covalent hydrides. First, covalent hydrides are usually soft. They are soft because of the force of attraction between their molecules is very weak. These weak intermolecular forces are referred as van der Waals forces of attraction. Second, they have low melting point and boiling points due to weak van der Waals forces. These forces are overcome very easily when some heat is provided to the compound. The exception are the hydrides of some p block elements like H2O, NH3, and HF. This is because these hydrides are partially polarized. This partial polarization happens due to the high electronegativity difference between oxygen, fluorine, nitrogen, and hydrogen. This partial polarization is so high that the negatively charged oxygen, fluorine, and nitrogen begin to attract positively charged hydrogen of other molecules. This leads to formation of a much stronger bond called hydrogen bond. Due to this strong hydrogen bonding, melting point and boiling points of these hydrides is much higher when compared to other covalent hydrides. Covalent hydrides also do not conduct electricity. This is because covalent compounds don't have ions, so they are unable to conduct electricity. Next is uses of covalent hydride. First, nickel hydride used in NiMH batteries. Second, palladium hydride electrodes in cold fusion experiments. Next, lithium aluminum hydride, a powerful reducing agent used in organic chemistry. Sodium borohydride, selective specialty reducing agent, hydrogen storage in fuel cells.
So next, we are going to move on the scandium hydride. So scandium hydride, known as scandium hydrogen alloy, which an alloy made by combining scandium and hydrogen. Hydrogen act as hardening agent, prevent dislocation in the scandium atom crystal lattice from sliding past one another. Scandium hydride with increased hydrogen content can be made harder than scandium. It can be formed by progressive hydrogenation of scandium foil with hydrogen. So the picture shows the elemental scandium. Next, it is about the synthesis of scandium hydride. Scandium hydride synthesis by hydrogenation of a scandium foil with hydrogen fluid under high pressure at ambient temperature. So scandium dihydride and trihydride were prepared near 4 and 5 GPa respectively. So the GPa is referred to the pressure, the unit of pressure. So at room temperature, the most stable form of scandium is the hexagonal close-packed HCP structure of a scandium. If scandium hydride contains more than 0.89% hydrogen at room temperature, then it transforms into a face-centered cubic structure, the alpha phase. So this picture shows the FCC structure.
Titanium dihydride is a dark gray powder. It is used to produce very pure hydrogen and silicides, borides, or titanium nitrides. Actually, we do not deal with individual titanium dihydride in practice, and the solid solution of hydrogen in titanium is called titanium dihydride, the composition of which you see on the screen. This is a non-stoichiometric material. The more hydrogen it contains, the darker titanium hydride powder is. Unlike highly flammable titanium metal powder, titanium hydride powder burns much more poorly in the air. However, it reacts with oxidizing agents quite violently. Therefore, it is often used in pyrotechnics to create white sparks. Now you can observe a reaction between titanium hydride and ammonium perchlorate. I showed some reactions with the latter in one of my previous videos.
So next we are going to move on the titanium hydride. Titanium hydride normally refers to the inorganic compound TiH2. The titanium hydride related to the non-stoichiometric materials. It can absorb 3-weight hydrogen gas, and the absorption of hydrogen embrittlement the titanium, which is the titanium is getting brittle when exposed to hydrogen. So the titanium literally fractures when exposed to hydrogen gas and elevated temperature. It is extreme form of hydrogen embrittlement. So the properties of titanium hydride. The inorganic compound titanium hydride related to the non-stoichiometric materials is commercially available as stable gray or black powder. It's insoluble in water. And the reaction of titanium hydride is slowly attacked by strong acids and degraded by hydrofluoric and hot sulfuric acids. It reacts rapidly with oxidizing agent, lead to the use of titanium hydride in pyrotechnics. The material has been used to produce highly pure hydrogen, which release upon heating the solid starting at 300 degrees Celsius. So the last is dissociation complete at the melting point of titanium. Titanium tritide has been proposed for the long-term storage of tritium gas. So the production of titanium hydride is commercially process of producing non-stoichiometric titanium hydride. So the picture in the left side is referred to the commercial process of titanium hydride. The titanium metal sponge is treated with hydrogen gas at atmospheric pressure between 300 to 500 degrees Celsius. The absorption of hydrogen is isothermic and rapid, change the color of sponge gray, and the brittle product is ground to powder, which has composition of titanium hydride. So next, the titanium hydride produced by heating titanium powder under flowing hydrogen at 700 degrees Celsius, which titanium react with hydrogen gas and produce titanium hydride. So titanium hydride produced by electrochemical and ball milling methods also. And the last one is about the uses of titanium hydride. It's for production of alnico-sintered magnets. It's referred to the left pictures which show the magnets, the sintering powdered metals. So it produces the metal from powdered titanium metal in pyrotechnics, and it's also from ceramics and sports equipment and as a laboratory reagent and also as a blowing agent, which below the slide, and it also produce a strong alloy when titanium hydride release hydrogen, which serve to remove carbon and oxygen.
Okay, next is vanadium hydride, VH2. Vanadium extracted from several different types of mineral deposits and from fossil fuels. The metallic vanadium has an excellent hydrogen storage properties in comparison to other hydride forming metals such as titanium, uranium, zirconium. Has shown high hydrogen solubility and diffusivity at nominal temperature and pressure conditions. Vanadium reacts directly with hydrogen at atmosphere pressure and room temperature to form production stoichiometric monohydride. Okay, next is synthesis of vanadium hydride. Vanadium was prepared by thermal decomposition and subsequent hydrogenation of tetraphenyl vanadium and evaluated for electrochemical. Vanadium reacts with hydrogen at high temperature and have examined the system in terms of pressure, temperature, and composition relationship and have derived from this data appropriate thermodynamic function and phase boundary. Okay, next we will look at the uses of vanadium hydride. First, vanadium hydride used primarily in the production of steel alloys, which is act as catalyst for chemical industry. Vanadium hydride also used for making glass, ceramics, and pigments. And lastly, vanadium hydride also act as catalyst for ammonia synthesis. So as you can see the picture below, the first is the production of steel alloy and the second is ceramics. Next element is chromium 2 hydride, CrH2. Chromium 2 hydride, also known as chromium dihydride and polydihydrochromium. It is pale brown solid inorganic compound with the chemical formula CrH2 in bracket N, also written CrH2 only. Although it is thermodynamically unstable toward decomposition at ambient temperatures, it is kinetically metastable. Chromium 2 hydride is the second simplest polymeric chromium hydride after chromium 1 hydride. In metallurgical chemistry, chromium 2 hydride is fundamental to certain forms of chromium hydrogen alloys. It have been isolated in solid gas matrices. The molecular hydrides are very unstable toward thermal decomposition. Chromium 2 hydride is the major primary product in the reaction of laser ablated chromium with molecular hydrogen. In the presence of pure hydrogen, dihydrochromium readily converts to bis dihydrogen dihydrochromium CrH2 in bracket H2 2 in an exothermic reaction. Next is properties of chromium 2 hydride. The properties can be separated into two, which are acidity and structure. For acidity, electron pair of Lewis base can join with the chromium center in chromium 2 hydride by adduction. Chromium 2 hydride has Lewis acidic character because of the capture of an adducted electron pair. It also is a strong Lewis acid with the capacity to capture at least 5 electron pairs of Lewis bases. Okay, next is the structure. In diluted chromium, in bracket 2, the molecules are known to oligomerize, forming at least dichromine, in bracket 4, which is dimers, being connected by covalent bonds. Dissociation of enthalpy of dimer is estimated to be 1 to 1 kJ per mole. CrH2 is bent and is weakly repulsive to one hydrogen molecule but attractive to two molecules of hydrogen. So next is synthesis of chromium 2 hydride. Dichromine is produced synthetically by hydrogenation. In this process, chromium and hydrogen react according to the reaction. chromium react with hydrogen, forming chromium 2 hydride. This process involves atomic chromium as an intermediate and occurs in two steps. The hydrogenation is step 2 is a spontaneous process. First, chromium in solid state converted into chromium in gaseous state. Second, chromium in gaseous state react with hydrogen in gaseous state, forming chromium 2 hydride. In a gas matrix, atomic chromium reacts with hydrogen to make the dihydride when it is irradiated with ultraviolet light between 320 and 380 nanometer. The reaction of chromium with molecular hydrogen is endothermic reaction. Okay, next is uses of chromium 2 hydride. First, chromium 2 hydride act as sazwani agent. The second is chromium 2 hydride used to make stainless steel. Next is chromium 2 hydride used to color glass green. Other than that, chromium 2 hydride help to form bricks and shapes. And last but not least is chromium 2 hydride also sometimes used for paint. So as you can see the picture below, the first one is sazwani agent, the second one is stainless steel, and the third one is paint.
Nickel hydride is either an inorganic compound of the formula NiHX or any variety of coordination complex. Nickel hydride is stronger than nickel metal due to the increases of hydrogen atom, but nickel hydride is also less ductile than nickel metal. Nickel hydride was prepared in beryllium copper high pressure cell at room temperature by applying a hydrogen gas pressure of 7 kilobar to pellets pressed from fine nickel powder. Nickel hydride is used as nickel metal hydride battery, which is type of rechargeable battery. Nickel metal hydride have higher power and energy density. Nickel metal hydride also completely safe and their power output is not affected by the battery energy state of charge. The nickel metal hydride are very expensive and it has higher self-discharge rate, low temperature operation, and higher cooling requirement. Copper hydride is a pyrophoric and inorganic compound with the chemical formula CuHN. It is an odorless red solid and rarely isolated as a pure composition that decomposes to the elements. Copper hydride is mainly produced as reducing agent in organic synthesis. Copper hydride is a alloy mixture of copper and atomic hydrogen. It is being connected by covalent bond. The oxidation state of the copper in copper hydride is positive 1. Copper do not react with hydrogen even on heating. Thus, copper hydride are made indirectly from copper 1 and copper 2. For example, the reduction of copper 2 sulfate with hypophosphoric acid. This reaction produces a red color precipitate of copper hydride. Copper hydride is also produced by reductive sonication. In this process, hexa-aqua-copper 2 will react with hydrogen in situ from homolytic sonication of water to produce copper hydride and oxonium according to this equation. Copper hydride generally behave as source of anion hydrogen. Chemical reaction for copper hydride. First, the double displacement reaction of copper hydride with hydrochloric acid, which is produce copper chloride and hydrogen gas. The second reaction is when not cooled below -5 degrees Celsius, copper hydride will decompose to produce hydrogen gas and a mixture containing elemental copper. It is according to the second chemical equation. Solid copper hydride is the irreversible auto-polymerization product of the molecular form, and the molecular form cannot be isolated in the concentration. Zinc hydride is an inorganic compound with the chemical formula ZnH2. It is appearance in a white crystal and a odorless solid, which is slowly decomposed into its element at the room temperature. The zinc hydride is the most stable of the binary first-row transition metal hydride. Zinc hydride is used as the reducing agent in organic synthesis. Structure of zinc hydride. Zinc hydride is a polymer that being connected by covalent bond. Solid zinc hydride is the irreversible auto-polymerization product of the molecular form, and the molecular form cannot be isolated in concentration. Zinc hydride is non-aqueous solvent. The stability of zinc hydride. Zinc hydride is slowly decomposed to the metallic zinc and hydrogen at room temperature, with decomposition become rapidly if it is heated above 90 degrees Celsius. Zinc hydride will be hydrolyzed slowly by zinc hydride. Zinc 2 hydride was first synthesized in 1947 by Hermann Schlesinger via a reaction between dimethyl zinc and lithium aluminum hydride. This process will produce zinc hydride. The second synthesis is salt metasis reaction between zinc halide and alkali metal hydride. For example, zinc bromine react with lithium hydride will produce zinc hydride and lithium bromine, or zinc iodine will react with sodium hydride will produce zinc hydride and sodium iodine, or zinc iodine react with lithium aluminum hydride, which produce zinc hydride and aluminum hydride and lithium iodine.